In the book AI L4IR, Leadership and the Fourth Industrial Revolution, the author Kent Kaufman discusses many aspects in the history of natural language processing and LLMs, or large language models. In the following short video, he discusses breakthroughs which are addressing cracks in the LLM facade as this area of AI rapidly advances.
The landscape of artificial intelligence is undergoing a dramatic transformation as we move beyond traditional large language models. The year 2025 marked a crucial turning point, revealing both the limitations of conventional LLMs and the emergence of 5 groundbreaking architectures that address these constraints. This shift comes at a time when the limitations of current LLM technology have become increasingly apparent, particularly in their tendency to confidently generate incorrect information and struggle with complex reasoning tasks. The fundamental challenge with traditional LLMs lies in their core mechanism, autoregressive next token prediction. While this approach excels at generating fluent text, emails, code, and stories, it suffers from compounding errors, inability to plan or backtrack, inevitable hallucinations, slow sequential processing, and lack of a true understanding of the physical world. As Jan LeCun notably observed, it's comparable to a parrot mastering chess notation without understanding the board. The autoregressive nature means errors compound as the model generates text, with one small mistake early on potentially derailing the entire output. The first major breakthrough came with JEPA, Joint Embedding Predictive Architecture, which introduced genuine world models. Unlike LLMs that simply predict next tokens, JEPA learns like a human infant by observing and internalizing fundamental concepts like gravity and cause-effect relationships. The 2025 releases were particularly significant. VJEPA 2 enabled robots to plan through mental simulation in new environments. LeJEPA introduced SIGREG to eliminate representation collapse without relying on fragile workarounds. And VLJEPA achieved superior performance in multimodal reasoning tasks by going beyond simple text prediction to understand the physical world. Liquid foundation models emerged as the second breakthrough, addressing the speed and resource limitations of traditional LLMs. These models employ dynamic weights governed by differential equations, enabling real-time adaptation to continuous data streams. The LFM2 series demonstrated impressive performance on CPUs, handling extensive contexts with minimal memory requirements, making powerful AI accessible on personal devices. This advancement particularly addresses the frustrating multi-second lag times common in current LLM interactions, enabling more natural, fluid conversations and responses. The third innovation came from Versus AI with active inference, fundamentally changing how AI systems interact with their environment. Instead of passive response to prompts, these systems actively explore, test hypotheses, and self-correct in real time. The 2025 demonstration showed remarkable efficiency, with robots mastering complex tasks using 90% less training data compared to traditional reinforcement learning methods. This breakthrough enables AI to take initiative, ask clarifying questions, and explore possibilities independently, rather than simply responding to direct prompts. Neurosymbolic AI represented the fourth breakthrough, combining neural network intuition with classical symbolic logic and knowledge graphs. This hybrid approach made hallucinations mathematically impossible, leading to increased adoption in critical sectors like healthcare, law, and autonomous driving where accuracy and trust are paramount. The system's ability to ground every output in formal rules ensures factual accuracy, addressing one of the most significant limitations of traditional LLMs, their tendency to generate plausible sounding but incorrect information. The fifth breakthrough came in the form of neural circuit policies, NCPS, bio-inspired sparse networks that offer unprecedented transparency in AI decision-making. Based on simple organism nervous systems, NCPs allow for neuron-by-neuron tracing of decision paths while consuming significantly less power, up to 1,000 times less than traditional systems. This advancement is particularly crucial for applications in safety-critical systems where understanding and auditing AI decisions is essential. These developments signal a shift from monolithic LLM architectures to specialized intelligences optimized for specific tasks, while LLMs maintain their advantage in creative text generation. The new architectures have demonstrated superior performance in common sense reasoning, efficiency, agency, factual accuracy, and safety. The practical implications extend across numerous fields, from robotics to medical devices and industrial applications. The practical implementations of these breakthroughs are already visible in the market. VGPA 2, LFM2 series versus robotics, neurosymbolic production systems, and sparse NCPs have moved beyond the prototype stage and are now in active deployment with continuous improvements. This represents what many are calling an AI Cambrian explosion, a rapid diversification of artificial intelligence approaches, each evolved to excel in its particular domain. Looking ahead, the key question for AI implementation becomes whether to continue scaling traditional token predictors or to embrace a portfolio approach with specialized intelligences tailored to specific tasks. The future points toward diverse, task-specific AI systems. Some optimized for physical understanding, others for instant on-device processing, autonomous exploration, guaranteed truthfulness, or safety-critical applications. This specialization allows for more efficient and effective AI solutions across different domains. This technological evolution represents not just an improvement in AI capabilities, but a fundamental shift in how we approach artificial intelligence. The limitations of traditional LLMs have sparked innovation in multiple directions, leading to more robust, efficient, and trustworthy AI systems. As these new architectures continue to mature and evolve, they promise to address many of the frustrations and limitations that have characterized the LLM era, opening new possibilities for AI applications across various domains, from healthcare and law to robotics and autonomous systems. The year 2025 stands as a pivotal moment in AI development, marking the clear transition beyond traditional LLM architecture and toward more sophisticated, specialized, and capable AI systems. These advancements suggest a future where AI can not only generate text, but truly understand, reason, and interact with the physical world in ways that were previously impossible with conventional LLM approaches. In conclusion, the pathway to high-efficiency AI and ultimately AGI, or artificial general intelligence, will require new architectures and new scientific breakthroughs. The future will be filled with great promise and uncertain dangers. However, it is clear that AI will soon go beyond large language models, which are currently transforming all of industry and society as science and technology move relentlessly forward towards this AGI goal.
Kent Kaufman, the author of the book AI L4IR, Leadership and the Fourth Industrial Revolution, has over 30 years of experience in executive roles, management consulting, and executive coaching. He has coached and mentored many Silicon Valley CEOs and top management teams. His book is available through Amazon, Barnes & Noble, and Ingram Spark, and his audiobook is on Spotify.